Okay, it's Brian. We're going to be talking about oscillations today. That is the material of chapter 14. So I want you to read chapter 14. And in chapter 14, we talk about simple harmonic motion. Now, it turns out there's a lot of things in nature that can be analyzed as simple harmonic motion. For instance, one of the systems we talk about is a mass on a spring. Well, a mass on a spring is like a car bouncing up and down on its springs for sure. But also when you run, you get a little bit of mass on spring motion due to your stretchy Achilles tendon. Other animals do a lot more than that, including rams, which is something we'll talk about at our in-person section. The other oscillatory system we'll look at is pendulums. And pendulums is like the classic case is the pendulum clock, but also we have gibbons as they locomote. They're basically swinging from one handhold to another. A gibbon is basically a pendulum. It is a mass that is swinging through some sort of an arc, like so. Gibbon is a pendulum, and your legs are pendulums when they move. And so there's a lot of things in the world around us that can be analyzed by thinking about simple harmonic motion. That's the type of thing we're going to be looking at today. Now, we're going to look at two basic systems that do simple harmonic motion. And in both cases, you have an equilibrium position. So if I have a mass on a spring, if we look at a case where the spring is not stretched and is not compressed, the mass is at equilibrium. And if we move it right or left of its equilibrium position, the spring is going to pull it back toward equilibrium. But once it gets there, it's going to keep on going. And so you have an oscillation. Same thing with a pendulum. If you have a mass on a spring or a mass on a string, it's going to be hanging at its lowest point. That's its equilibrium position. But if I pull it to the side, it will swing back to where it came from, and then it will keep on swinging back and forth. And so again, I have that oscillatory motion. So in both cases, I've got equilibrium, and they have a restoring force that pushes back toward equilibrium. Now, it turns out there's a breathtaking number of systems in nature that you can analyze this way. And the really amazing thing about them is all of them have similar motion. The mathematics of them are identical. So if we can analyze something by treating it as simple harmonic motion, we have all kinds of techniques that carry through. And the two basic cases we'll look at, and we'll model so many things as that is either a mass on a spring or a pendulum. We'll be talking about those today. There's two key properties whenever you have simple harmonic motion. So if you have regular motion, we're going to talk about it in terms of position, velocity, acceleration. But if you have oscillatory motion, the two things you're going to be interested in are, one, the frequency, or the period, which is how many cycles per second or how many seconds per cycle. Basically, how much time does it take to complete an oscillation? Number two is the amplitude. How big is the oscillation? And if I know the frequency and I know the amplitude, I have completely characterized a system in simple harmonic motion. So it's a very small number of quantities to be able to completely characterize a system. Now, it turns out the frequency of simple harmonic motion is determined by physical properties of the system. If it's a mass on a spring, it's the spring constant k and the mass m. If it's a pendulum, it's the length L and the value of gravity g. But, for us, gravity is basically the same. So wherever you go, so we're not going to have to worry about that. So it basically just varies with the length. The amplitude is determined by whatever set it in motion. Now, something to be aware of is that the frequency of an oscillatory system is independent of the amplitude. So these two quantities, the amplitude and the frequency, are independent of each other. And that's why pendulums are useful in clocks. It doesn't matter how far the pendulum swings back and forth. The time for it to swing back and forth is always the same, and it's just a function of its length. So if you can accurately measure a length, you can make a pendulum clock, and that's why the first really accurate clocks were pendulum clocks. But the same is true of the mass on a spring. The amount of time to go back and forth is independent of how far it moves. Now let's take a look at the details of oscillatory motion, and this is treated in chapter 14, but I want to think about the position or the displacement. I want to think about the velocity, think about the acceleration, but also think about kinetic energy and potential energy. And energy is a useful lens through which to view simple harmonic motion. So I want you to think about this. For the system sketched above, question, at what time or times is the displacement zero? At what time or times is the velocity zero? How about the acceleration? And then think about at which time or times is the kinetic energy a maximum and the potential energy, when is that a maximum? I want you to look at this. I want you to think about those 5 questions in turn. I'll be back and discuss them with you. Okay, now I know you haven't actually paused the slides. You're just going to wait for me to tell you what's what. But you need to be active to get the most out of these slides that I post. I want you to pause right now, try to answer these 5 questions, and then I'll be back. Now first, if the displacement is 0, well, the equilibrium position is given right here, okay? So if the ball is at equilibrium, which it is in these cases, A and E and I, for those 3 cases, the ball is at equilibrium, and so that is the cases where the displacement is 0. When is the velocity 0? Well, the velocity is 0 when the ball is at its lowest point of its motion and at the highest point of its motion. It temporarily stops moving as it's reversing direction. The acceleration is going to be equal to 0 when the force is equal to 0. And think about this. If this point right here is the equilibrium position, there's no net restoring force because that's its happy place. And so at points A and E and I, the restoring force is 0. And so as a consequence, the acceleration is equal to 0. So when it's passing through equilibrium, the acceleration is equal to 0. The acceleration is a maximum at the lowest and the highest point of the motion. The velocity is 0, but it won't stay that way. It quickly switches to going in the other direction. Now let's think about energy. The kinetic energy is when it's moving fastest. Okay, and it's moving fastest when it's going through equilibrium. So A and E and I, those are cases where the kinetic energy is a max. The cases where the potential energy is a maximum are cases C and G. Now in case G, I've got gravitational potential energy. In case C, I've got elastic potential energy or spring potential energy. And so as this simple harmonic oscillator goes through its cycle, the energy goes from kinetic to potential, back to kinetic to potential, and back to kinetic. And so you're really transferring energy back and forth between those 2 different modes. And that is useful in the context of locomotion, which is something which we'll talk about at our in-person section. Suppose we consider a pendulum and we ask the same questions. I want you to take a look at each of these questions in turn and apply them to the case of the pendulum. So pause the video, think about how you apply those. I'll be back. Well, the first question asks, when is the displacement 0? Well, the displacement is 0 at the equilibrium position. That is case C and G. When is the velocity 0? The velocity is 0 at the points where the motion is reversing. So at A and E and I, the pendulum has gone as far as it's going to go to the side, and the velocity is 0, and then it's going to immediately switch direction. When is the acceleration 0? That is 0 as before when the amplitude is 0. When the displacement is 0, because then the ball is at its equilibrium position. There's no restoring force, and so no acceleration. When is the kinetic energy maximum? In the center. So when the ball is at the center position, when it's at equilibrium, it's moving through the equilibrium position and it's moving at a maximum speed. And so as a consequence, the kinetic energy is going to be a maximum at those points. When is the potential energy a minimum? Well, that's when the ball is the highest up, and that's when it's furthest to the side. And so in this case, as in the previous case, we have a situation where the energy goes from potential to kinetic to potential to kinetic and back to potential. And so I have an oscillation in which I have energy being transferred back and forth between those different modes. Now there's a functional description of simple harmonic motion which is presented in the textbook, and you can use the sine and cosine functions for that. The main thing we're going to be interested in is this. We know that the position, the velocity, the acceleration all vary according to these sinusoidal functions. We're going to be interested in the amplitude and interested in the maximum values of those. The maximum displacement from equilibrium is the amplitude. Okay, so that's how far the object is from its equilibrium position. That's how we define it. The maximum velocity is the amplitude times 2 pi times f, where f is the frequency. The maximum acceleration is 2 pi times the frequency squared times the acceleration. And we will use these three relationships extensively in the problems we're going to solve. One other thing we're going to use, one other set of mathematical relationships, are the ones that relate the period or the frequency to the physical properties of the system. For a mass on a spring with spring constant k and mass m, the frequency is 1 over 2 pi times the square root of k over m, or the period is 2 pi times the square root of m over k. If I'm looking at a pendulum, the frequency is 1 over 2 pi times the square root of g over L, where L is the length of the pendulum, or the period is 2 pi times the square root of L over g. Now let's look at a classic simple harmonic motion problem. Okay, so we have some details here, so take a second to look that through. If we were in person, I would actually do this. I have a spring and a 250 gram mass, and if I take that mass and I pull it downwards so the spring stretches, it requires me to supply a force of 1 Newton. So as a consequence, the spring is pulling back with a force of 1 Newton. So if I let the mass go, it'll rise upward, but then as the force goes to 0, the mass is going to be picking up speed, and so it will move through the equilibrium position, and then it will oscillate, as we've seen. So it will go through some sort of a cycle where it starts at its lowest point, and then it goes up, and it goes through its equilibrium position, keeps on going, reaches its highest position, and then comes back down, and so on. It's going to kind of go through some sort of a cycle, as we have seen. Okay? And we have two questions. One is, how long will it take the mass to return to its starting position? And two, what is the maximum speed of the mass? Now to solve this, first we're going to strategize. And the strategy we're going to say is we're going to treat this as simple harmonic motion. And so as a consequence, we can use all the technology that we've developed to solve this type of problem. For a preparation step, what I'm going to do is this. I'm going to draw a graph of the motion as a function of time. Now I've taken this mass and I pulled it down to a position 10 centimeters below its equilibrium position, or 0.10 meters. Okay? And then I let it go, and the mass is going to rise up to its highest point, and then it's going to come back down to its equilibrium position. That is one complete cycle of the motion, and we can see that. So the first question, how long will it take the mass to return to its starting point? That is just basically saying what is the period for the motion. Okay, we can say that. And the second piece, what is the maximum speed of the mass? Well, we're just looking for V max. One other thing we can do by way of preparation is we can say this. Pulling the mass down by an additional 10 centimeters takes a force of 1 Newton. We can use that to compute what the spring constant is, because remember, the restoring force of a spring is equal to, or the magnitude of the restoring force is equal to k times delta x, where delta x is the stretch of the spring. So we requires a force of 1.0 newtons for a stretch of 0.10 meters, and that tells me that the spring constant is equal to 10 newtons per meter. And that will be an important piece of data which we'll use in solving the problem, which we're ready to do right now. Now to solve, we're going to say this. How long will it take the mass to return to its starting point? Remember, we said that's just the period. And the period for the mass on a spring is equal to 2 pi times the square root of m over k. Okay? And we know what those values are. The mass, 250 grams, or 2.250 kilograms, and the spring constant is 10 newtons per meter. And if we solve that out, what we get is 0.99 seconds, which is approximately equal to 1 second. Okay? That's what we're going to get for our first piece of the puzzle. The second piece asks, what is the maximum speed of the mass? And remember, we had an expression for V max for something in simple harmonic motion, and that was equal to 2 pi times the frequency times the amplitude. Now the amplitude of the motion is this. The amplitude is how far is the mass from equilibrium. Well, from equilibrium, we've pulled it down by 10 centimeters, okay? And so since we've pulled it down by an additional 10 centimeters from its equilibrium position, our amplitude is just 0.10 meters. If the period is 1 second, the frequency is equal to 1.0 hertz, because frequency is equal to 1 over period. That's something we learned back when we were talking about circular motion. So the frequency, 1.0 hertz, the amplitude, 0.10 meters, and so if we work out what the maximum speed is, we get 0.63 meters per second. Okay? Now for assessment, what I would do in person is this. I would just say, let's take that system, which I actually have, and just let it go and kind of like estimate the period and estimate the speed. And it turns out our assessment is everything works out about like we calculated, as indeed it must. But I want to do more than just like very, very abstract and arbitrary systems like that. Because simple harmonic motion is all around us, it turns out buildings are flexible. If you take a building and you push it to the side by like blowing on it with the wind, there's a restoring force that wants to push it back to where it came from. It works like a mass on a spring. And so we can analyze the swaying of a building by using simple harmonic motion. And so our strategized step is we're going to treat this as simple harmonic motion. Now let's do some preparation. This problem is asking us to figure out the total distance side to side that the top of the building moves for such an oscillation. Well, if the top of the building is moving side to side, let's draw a graph of the motion of the building, okay? And it moves side to side. It's going to be oscillating like so. That's a graph of simple harmonic motion. Well, if it starts out here and ends up here, starts out at A, ends up at negative A, the total magnitude of the displacement is just 2 times A, 2 times the amplitude of the oscillation, okay? Now, we're told that it sways with a frequency of 0.17 hertz, and we're told the acceleration is 0.02 g. Let's go ahead and calculate that out. The acceleration reaches 0.02 g, and let's just assume that's the maximum acceleration. So A max is equal to 0.02 times g. 0.02 times g is equal to 0.196 meters per second squared. Okay? And I think with that, we pretty much have everything we need to do our next step, which is to solve. Now our solution says this. Okay, A max, which is equal to 0.196 meters per second squared, is also equal to 2 pi f squared times the amplitude. Oh, I mean, because that's our basic relationship for A max. Well, I know the value for A max, and I have an expression for A max that only depends upon the frequency and the amplitude. I know the frequency, that's 0.17. The amplitude is what I'm looking for. And so with all that in hand, I can solve for what the amplitude is. And if I do that, I get a value for the amplitude, 0.17 meters. But the distance side to side is going to be 2a, and 2a is equal to 0.34 meters. That's a little bit over a foot. That's a little bit over a foot, which seems sort of surprising. But in fact, if we assess by actually looking at data for how much buildings sway, that's very reasonable. You want your building to be able to sway. You want it to bend and not break. That's an important thing for structural stability. So this 1 foot distance side to side is kind of surprising. Top of the building sways one way, sways the other. Total distance side to side is about 1 foot. That's reasonable. And then think about this. If you were in a building that was swaying back and forth side to side and the frequency was 0.17 hertz, so it's taking about 6 seconds to do that, to sway and do 1 complete cycle, I would feel nauseous. And in fact, people at the top of the building do. And on super windy days, people go home because it's just not comfy. Now we want to look at some other situations, and I want to look at one of this creature here called a hawk moth. And if we were in person, you would be seeing this hawk moth actually going. If you look at the motion of its wings, it's actually going up and down, basically as simple harmonic motion. And you can actually hear them. It makes kind of a little low tone. These things show up in my garden all the time, and you can actually hear their wing beats. It's kind of crazy. And we have a question about them. And what we want to know, for the data given for the motion of their wings, we want to know the maximum velocity and the maximum acceleration of their wingtips. Okay? That's what we want to look at, given the data in the problem statement here. So go ahead and take a look at that. We'll continue. Now first, I'm going to do my strategize. And my strategizing, as always, I'm going to say we're going to treat this as simple harmonic motion. And my preparation is to characterize the motion. And the first thing I'm going to do is I'm just going to draw a graph of the motion of the wingtips. Okay? And we're told they move up and down by 5 centimeters from their central position. So the wing moves up by 5 centimeters, and then down by 5 centimeters, and then back to the central position. Okay? And what that's telling me is the amplitude of the motion, because it goes from A and then goes to negative A, the amplitude is equal to 0.050 meters. That is the amplitude of the motion. And the frequency of the motion is 26 cycles per second. Given those numbers, we can calculate those two pieces of information, the maximum velocity and the maximum acceleration. And the maximum velocity, Vmax, is equal to 2 pi times f times the amplitude. Amax is equal to 2 pi times the frequency squared times the amplitude. And if we calculate both those numbers, what we get is a maximum velocity of 8.2 meters per second and a maximum acceleration of 1,300 meters per second squared. Now, let's do some assessment of those numbers. So first off, I want to think about the maximum velocity. Well, a hawk moth can't move any faster than its wingtips move, because it's basically pushing back around the air. And we came up with 8.2 meters per second. Can these things move at 8.2 meters per second? Yes, they can. They can't move much faster. They don't move as fast as like cars move down my road, but they definitely move more quickly than I can move. They're very, very zippy creatures. So my assessment about the maximum velocity of the wingtips seems quite reasonable. Now the other one, a maximum acceleration of 1,300 meters per second squared, seems kind of amazing. That's 130 Gs. But they're moving up and down through a total distance of 10 centimeters, and they're doing that 26 times a second. That's a lot of changes of speeds because you're moving upward at 8.2 meters per second, and then a 52nd of a second later, you're moving downward at 8.2 meters per second. That is an intense acceleration. And so these things look like they're delicate, but they are robust. Their wings are very, very strong indeed. So my assessment is, yeah, this is kind of surprising, kind of amazing, but yeah, that is how the world works. Now, another property of simple harmonic motion we want to look at is resonance. If you have some sort of system which is driven, okay, if it's got a certain frequency it likes to oscillate at, and you drive it at that frequency, you get the maximum possible amplitude when you drive it basically at its resonance frequency. Systems have certain frequencies they like to oscillate at, and if you drive them at the frequency they like to oscillate at, you get much bigger oscillations. Kind of makes sense. Kind of makes sense. And I'll give you an example of this. When Milo pants, he's driving air in and out of his body. And when he does that, there's a certain mass in motion. It's mostly like the mass of the lungs and the diaphragm and all that kind of like tissue. That's oscillating back and forth. And it turns out it's very springy tissue. So there's a mass which is moving basically as a mass on a spring. this has a certain frequency of oscillation. Milo has a certain resonant frequency at which he pants, and the muscles drive the panting at that frequency. And so he can move air in and out very, very efficiently. He gets lots of motion for a very small energy input because he's doing it at a particular resonant frequency. And all dogs work like this. And you work like this too. Your arms and legs basically work like pendulums. When you're walking, you want your arms extended. They're out straight. But when you're running, you're moving your legs more quickly. And so you want your arms to be basically oscillating in step with your legs. And so you take your arms and you shorten them up. Shorter pendulum, higher frequency. The frequency matches the new frequency of your legs. Now I want to talk about a resonance problem, and this is one that I observed when I was driving my car, whose name is Casper. It's like Casper the Friendly Ghost because he's white. Anyway, I'm driving Casper down a corrugated road, and a corrugated road is one that has bumps just like this. Okay, and you've been down roads like this. So I'm driving down a corrugated road, and Casper is bouncing up and down on the springs. And then my question to myself was, should I drive slower or should I drive faster to give a smoother ride? And actually this, of course, is a physics question because Casper is a mass on a spring. There are springs on each of the four wheels. And so the Casper is going to bounce up and down at a certain frequency. And it turns out you can look up data for the motion of cars. And so I went to Toyota's website and I got actually data for the oscillation amplitude of my particular model of car as a function of frequency. And they take cars and they put them on plates that vibrate up and down, and they kind of like see what kind of amplitude of oscillation you get. And they found this data on Toyota's website because Casper is a scion, it's a mark of Toyota. And here's my question. Suppose I'm driving my car down the road at 10 meters per second. It's a washboard road with bumps spaced 3 meters apart. And this was the actual situation I encountered. And then the resulting ride was, in fact, quite bouncy. Here's the question. Should I speed up or should I slow down to give a smoother ride? Well, we're going to strategize first, of course, and we're going to strategize by treating this as a simple harmonic motion problem and specifically dealing with resonance. Because as we go across bumps, we are driving the car up and down on its springs. And so there's a driving frequency due to the motion of the car. And the question is just asking, is the driving frequency in resonance with the frequency the car likes to oscillate at or not? And what can we do to improve the situation? So, next piece of the puzzle, let's prepare. Now to prepare, what I'm going to do is this, okay? Driving down the road at 10 meters per second, and the bumps are spaced 3 meters apart. Well, let's think back to some of our kinematic expressions back from chapter 2. We know the distance traveled is equal to the velocity times the time interval, okay? So the time interval is equal to delta x over v. Now if I'm traveling at a speed of 10 meters per second and the bumps are spaced 3 meters apart, what that tells me is I'm hitting a bump in the road every 0.30 seconds. And since we're modeling this as simple harmonic motion, that's telling me the period at which I am driving the car up and down on springs is 0.30 seconds. That corresponds to a frequency of 3.3 hertz. Okay, and with that in hand, we're ready to solve. And solving looks like this. I'm going to look at my graph and I'm going to say I'm driving down the road and I'm bumping the car up and down on springs at a frequency of 3.3 hertz. And 3.3 hertz is right about there on the graph. And the question is, should I drive up or slow down for a smoother ride? Now let's think about this. If I go to a lower frequency, oops, I'm going higher and higher on the graph. I'm going to a higher amplitude of oscillation. That's not good. If I go to a higher frequency, I'm going to a lower amplitude because I'm not as close to being in a match with the actual frequency at which the car likes to oscillate. So if I want to go to a higher frequency, like if I can get up to like 6 cycles a second, okay, That would be a much lower amplitude of oscillation. That's like half what it was for 3.3. I'm going to hit the bumps at a higher frequency if I travel at a higher speed. So what you want to do is you want to go faster. And in fact, in this particular case, that's what I did. So my assessment is driving faster did in fact give me a smoother ride. The only downside was my tires weren't moving up and down as much because I was going pretty fast. So the tires' amplitude of oscillation is not very much. I'm hitting the bumps too quickly for the car basically to respond. It likes to respond at this frequency. I'm asking it to respond at this frequency. It just wasn't. So my tires weren't in contact with the road surface much of the time, which meant I wasn't able to steer or brake. So it wasn't a very safe ride. It wasn't easy to control, but doggone, it was smooth. So in fact, I just did that for a little while, and then I slowed down and drove at a much safer speed. And in fact, the thing to do is just to drive at a much slower speed. So go way down here. So just slow down, go real slow, go over the bumps. It's safe, it's smooth, everything's good. Now, one other place where we're going to see this, and I'm bringing this up because we're going to talk about this in chapter 15, is this. It turns out when you sense sound waves enter your ear that cause the eardrum to vibrate. They transfer the vibrations through this sequence of bones, and then they end up in the cochlea. In the center of the cochlea is this basilar membrane. And the frequency at which the basilar membrane likes to oscillate varies with position, and as you move further and further along it from where the sound comes in. So you have the stapes right here, and it vibrates, and then there's a vibration in the fluid, and as you move further and further along the stapes, the oscillation frequency changes. And it turns out the parts of the membrane right near the stapes tend to be very, very thin. They oscillate naturally at very, very high frequency, and as you go further and further along it, the frequencies are lower and lower. So the way that your brain distinguishes sound is you're going to send some vibration in the fluid, and you're going to see where along the stapes is the largest amplitude of oscillation. And here's actual data for the amplitude of oscillation as a function of distance along the basilar membrane for different frequencies. And you can see 300 hertz, I'm getting a lot of vibration right here. 100 hertz, I'm getting a lot of vibration right here further along. And so that's how you distinguish frequencies. And actually you can distinguish multiple frequencies at one time, which is something that we'll talk about when we talk about hearing. But before we can talk about hearing, we have to talk about waves. And so we're going to our next big topic is going to be waves. We're going to connect that with sound and ultimately connect it with hearing.